A presentation for the big data class. So this project is learning from sleep data, and this is for Team 56, which has just one member, myself, Mimi Wang. So first, I'll go through the background, and then I'll talk through the problem description. Then I'll talk about the approach that was used for this study, and then I'll talk about the results and some conclusions. So some background. So the CDC estimates that about 35.2% of all US adults suffer from sleep deprivation. And why that's important is sleep deprivation or poor health quality or poor quality of sleep has been linked to serious health issues such as heart diseases, obesity, and mental health issues such as depression. So one way for doctors to diagnose sleep issues such as apnea is through the usage of PSG or polysomnography data. So on a bottom graph, that's an example of what a PSG data looks like. So according to the American Sleep Association, there are 5 stages of sleep. And each of the stages refer to how deeply a patient is sleeping, and they all have unique PSG signatures. So you can go from not so deep, which is you're awake, to stage 1, stage 2, stage 3, and all the way to the deepest stage, which is REM sleep. And using doctors can diagnose common sleep orders by tallying the amount of sleep, the amount of time a patient spends in each of these stages during sleep. So the problem description. So currently, the most used methods of classifying sleep stages rely on visual inspections by human experts. So this is time consuming, it's expensive, and it's error prone. And studies have shown that there are large variations in the scoring of the same data between different experts. So the goal of this project is to derive a model for automatically classifying sleep stages using PSG data. And we want the performance to be comparable or better than those cited in literature, which is between 70% to 98% accuracy. So let's talk about the approach. So for this study, data from the ISRUC sleep site was used. The data set contains raw PSG data along with hypnograms or labels created by human experts. Time domain metrics were calculated for each PSG signal and used as the model features. So time domain metrics include calculating the mean, the median, and the standard deviation of the raw signal. Python and SciPy were used for parsing the raw data files and uploading them to AWS S3. The raw data files were in MATLAB format, so I had to use SciPy to parse that into CSVs. And then time domain features were calculated and joined with the labels using Spark via AWS EMR. So using Spark, we're able to load the parsed CSV raw files and then calculate the mean, the median, and standard deviation of each of the PSG signal, and then join that with the human experts labels. And then the data set was split into a 70% training set and 30% testing set. And these two sets were used to build and evaluate the random forest model, which is the classifier that was used for the study. So here are the results. So the model that yielded the best result had a max depth of 20 with 100 trees, and it yielded about an overall accuracy of 82%. So the plot below shows that increasing the depth or the number of trees beyond 20 and 100 did not yield any significant improvements. But if you look at the performance with a max depth of 10 and number of trees of 100, do you see a significant jump going from 10 to 20, about a 10% increase in accuracy? So here we have the confusion matrix in percent for the model. So it shows that generally the model is pretty accurate in terms of classifying the wake stage, stage 2, stage 3, and REM sleep. However, it only classifies stage 1 correctly about 49% of the time, and it misclassifies it as stage 2 20% of the time, and as wake 14% of the time. So for stage 1 in particular, this model did not perform very well. So here are some conclusions. So in this study, we're able to use fairly simple time domain features, the mean, the median, and the standard deviation, on just the raw PSG data to build a random forest classifier to achieve an overall accuracy of 82%, which is comparable to the methods that were cited in the literature. However, the weakness of this model is that we were only able to classify stage 1 with an accuracy of 49%. So some ideas for future works. We can look at additional time domain metrics such as kurtosis or skewness, or look into frequency domain metrics such as relative power. On the flip side, we might want to reduce the amount of features we're using by using dimensionality reduction, such as PCA or SVD, to get rid of the features that may not be relevant to classifying these sleep stages. And finally, we can look into using other classifiers such as CNN to build the model instead of using just the random forest. So that's the end of the presentation. Thank you for listening.